our last topic in this semester, to solve the linear system of linear differential equations. Instead, just one equation. Now we have a system equations. So the systems of ordinary differential equations, that means we have more than one component. What does that mean? What does that mean that we have more than one component? Let's consider the linear differential equation, second order. Okay, for this, I want to find the solution of y, right? We can think of x1 is y, and then x2, with that x2 equals y, x1 prime, then which is y prime. Then in this case we only have x1 and x2. Okay, so if we use x1, x2 to re-represent this differential equation, then we have x1 prime, because x2 is y prime, which means x1 prime equals x2. And then if I take the derivative of x2 prime, there'll be y double prime. And what is y double prime? Here. Okay. Then we can write this differential equation in a matrix form. So let's say this is equation 1. Now we want to find the solution of x1 and x2. So this is a system of two first-order linear differential equations. Rather than you need to solve the second-order differential equation. Now this is only first order, and we use the vector form with that x1 and x2 to put those two into a vector. Then for this equation, I can rewrite the equation 1 into the vector form. So x1 prime, x2 prime, x1 prime equals x2. So here if I have x1, x2, then I should put 1 here. And the x2 prime equals minus k over m times x1. So here I have minus k over m. The other one is minus r over m. So according to this vector form, now we can define, and first let's say this is equation 2. Now we can define the this x vector is x1, x2. And the matrix A, this will be x prime equals ax. So A is 0, k over m, 1 minus r over m. Then in that case, x prime is x1 prime, x2 prime. So the equation 2 becomes x prime equals ax. Then next step, we try to find x, the solution. All right. So according to this trick, having this second order linear differential equation into two first order linear differential equation, and I can also write it down the vector form into x prime equal to ax. According to this differential equation, also please write it down x prime equals ax. Then what is x, and what is a? Just using the same trick. Okay, first you need to let x equals y, x1, and then x2 equals y prime, and then you can write it down the matrix form. Let me give you 3 minutes to do it. Right, so now let's see. First is second order, right? So I know that I should have two variables, two state variables. So I will say x1 and x2. So x1 will be equal to y. Then x2 equals x1 prime. So here, follow the same procedure. We have just let the x1 equals y. Then x2 equals x1 prime, which is y prime. So once I have x1 and x2, we know x1 prime equals x2. And x2 prime, x2 prime will be y double prime, right? And y double prime, that will be 6t minus 3y prime minus 2y. And the y is x1, y prime is x2. So here I should have 6t minus 3x2 minus 2x1. Okay. Minus 2x1 minus 3x2 plus 6t. Now you have these simultaneous equations. We can write it down the matrix form or the vector form. So x prime, say x prime. What is x? X is consisted of x1 prime and x2 prime. So here x1, x2 prime. Then how do I express this matrix? x1 prime equals 1 times x2. So 0, 1. x2 prime equals minus 2x1 minus 3x2. Then I have minus 2 and minus 3. And then later on we have another vector 0, 6t. Okay. Any questions for this one? If not, then we will extend this concept to n-dimensional linear system linear differential equation. I have x1 prime, x2 to xn prime. So if I have x, this is a vector, including all the state variables x1 to xn, then here those coefficients can form a matrix A plus the term of G vector. This system can write it down as x prime equals ax plus g. This is in the vector form. We can also write it on this vector form as an index form. For index, you can just change this index to specific row or specific equations. So xi, for example, x1 prime. How do I express x1 prime? First, summation, because these terms, I can express these terms as a summation, plus the function g. And for this equation, let's say this will be equation 3. Okay, so here's the example. I still have two equations, x1 and x2. To express this as the simultaneous equations into the vector form, then x1 prime, x2 prime, here's x1, x2. Okay, what is the answer for this matrix A? What is the number? Anyone? x1 prime equals 3x1 plus 3x2 plus 8. And x2 prime equals x1 plus 5x2 plus 4e to the 3t. So this matrix should be what? What's the element? That's very important, because if you cannot write it down this matrix A, then how do you find the solution of x1 and x2? 3, 3, 1, 5. Right, because it's 3x1 and 3x2. So first it should be 3, 3, and the second row 1, 5. Okay. If I have initial conditions, say here's the initial conditions, x1 of t naught, then we put the subscript 0. So x1 0, x2 0. Then for this, I collect all these initial conditions, and then we can write it down as a vector, x t naught. And we say we have x, this is still vector, and sub 0. Okay. Then for this equation with the initial conditions, let's write it down again. Okay. So x prime, that consists x1 prime and x2 prime. What is the matrix A? All right, again, what is the matrix A? Okay, 1t cubed minus e to the t. For this expression, we can write it down. X prime equals a x plus g. And then for the initial condition, well, initial condition, that's 2 minus 5. So any questions so far? And then how do I know I have a solution or not? And if I have a solution, is that unique, or actually I can have multiple solutions? So here's the existence and uniqueness of the solution. The coefficient, and also what is g? Here this is g. Okay, if they are continuous, and in this case, this system, which is this one, okay, or here, this system has a unique solution with the initial condition. System 3 has a unique solution and this solution is defined for all time t in an interval I, and with here initial condition xi of 3 to n. So if you see the coefficients and also the forcing function g, they are continuous, then for that system I have a unique solution. Now for this system, okay, the system 3 is also like this. Then we try to find a solution. First, we will consider it without this forcing function g, which will be a homogeneous system. Remember that for the topic 1 and also in the beginning of this semester, we also talk about the differential equation with homogeneous type and also non-homogeneous type. So first we just consider the homogeneous one, and later on we will consider the overall. And you can expect for the overall I will have general solutions, homogeneous solutions, plus the particular solutions to form a overall general solution. Okay, but first let's just discuss the homogeneous system. X prime equals ax, and x prime equals ax means x is a solution that will satisfy that equation. And then x is a solution if I times a constant, it is also a solution. Okay. Suppose 1, 3, well, 1, 3 is a solution for 2 dimension. Then 2, 6 minus 1 minus 3 is also the solution that will satisfy this equation. Now, before we really need to find a solution, we also need to know some pre-knowledge. First, similar to what we have already learned in the beginning of this semester, first we need to learn what is the linear combination of solutions. If phi 1 to phi k, they are solutions of this homogeneous system, x prime equals ax. And I also have the coefficients within numbers c1 to ck. If phi 1, phi 2, phi k are solutions, then the linear combination c1 phi 1 plus c2 phi 2 to ck phi k is also a solution. Okay. Next, the linear dependence of the solution. We know x1 to xk are the solutions of this homogeneous system. And these solutions we call linearly dependent. If it is linearly dependent, that means one solution, maybe phi 2, is a linear combination of the others. I can write it down. Phi 2 will be the C1 phi 1 plus C3 phi 3 to CK phi k. So one solution can be expressed as a linear combination of the others. Then those solutions together we say they are linearly dependent. Just recall if I have a vector En that's C1 E1 plus C2 E2 plus C3 E3 TO C n minus 1 E n minus 1. Then we say if this vector En can be the linear combination of the others, then overall E1 E2 to En are linearly dependent. When we say linearly dependent, that also means we can say that equivalently if we can find C1, C2, those coefficients, they are not all zeros, then the vectors are linearly dependent. Not all zeros. Not all zeros means, oh no, not zeros, such that I can have C1 E1 plus C2 E2 plus Cn En. This is a zero vector. If it is zero vector, but those coefficients are not all zeros, maybe C1 is 0, C3 is 0, Cn minus 1 is 0, but C2 or Cn is not 0, then it has to be 0 for E2 and En. Then E1 to En are linearly dependent. So two ways to say those vectors are linearly dependent. That means one vector can be written as a linear combination of the others, or we say that the coefficients for their corresponding vectors are not all zeros. Some of them may be 0, but some of them are not. Then if they are not all zeros, the coefficients are not all zeros, then the vectors are linearly dependent. Well, if the coefficients are 0 to satisfy this equation, only when all the coefficients are zeros, then we say that the vectors are linearly independent. So if this linear combination equals 0 vector only when all the coefficients Ci is 0. In this case, then the vectors are linearly independent. All right, any questions for this review? All right, if you don't have any questions, then let's see some notes. Here are some notes. We say the solutions, well, now we back to our system's equation. Solutions phi 1 to phi k, we say they are linearly independent. If they are linearly independent, that means any one of this solution phi I cannot be written as a linear combination of others. Okay, I cannot figure out or find out a coefficients to that. For example, phi 2 equals phi 1 plus phi 3 to phi k. It doesn't work. I cannot find the coefficients to make this equation happen or valid. Then they are linearly independent. And for the system of a n linear differential equation, if I have n equations, okay, 1, 2, 3, 4, 5 till n, for this homogeneous equations, they are at most n linearly independent solutions, phi 1 to phi n. Because I only have n equations, like 3x1 plus x2 plus x3 equals 5. 2x1 minus 2x2 minus 4x3 equals 6. x1 plus 2x2 minus 3x3 is 7. When n equals 3. And for this solution, I can only find phi 1, phi 2 to phi 3. And most 3 linearly independent solutions. I cannot find phi 4. Phi 4 will be the linear combination of those previous 3. Okay. And then we may say the space spanned by phi 1 to phi n. You see that those phi is a vector. This is called the solution space. And this solution space is n-dimensional, n dimension. Now, if I find n independent vectors, any solution for these homogeneous systems can be written as a linear combination of phi 1 to phi n. So I can have another solution phi that is the linear combination of phi 1 to phi n. Because we know that suppose 2, 3 is a solution, 4, 5 is a solution, then 6, 8 is also a solution. And for the phi 1 to phi n, we will call that they are fundamental solutions of this homogeneous system. Now here's the question that we know. Okay, so if I know all this concept, I need to find if this is n linear differential equations, then I can have n linearly independent solutions, phi 1 to phi n. Okay, then two questions. How can I find phi 1 to phi n? And once I find n solutions, how do I know they are linearly independent? If they are not linearly independent, first, they are not fundamental solutions. And you may lose or miss some solutions that you probably don't know. Because if they are not independent, then maybe there's one more somewhere that you don't know. And if they are not independent, maybe that means one of your solutions can be written as a linear combination of the rest. So first, how can I find the n solutions? And the second, how do I know these n solutions are linearly independent? Right? So first, if we want to know they are independent, then we have a test. The test for linearly independence. Remember that in the beginning of this semester, we also learned that to test for the linear independence, there's a rock-sky test, right? The determinant is not equal to 0. And here, similarly, in linear algebra, I have E1 to En, and here's E1. That's the vector. They are linearly independent if and only if the determinant of the matrix, this matrix E, is formed by E1 to En. This matrix is non-zero, then these n vectors are linearly independent. So this is E. Okay, here's E1, E2 to En. So this is E1. E2. If I find n solutions, then I just form it as a matrix, and then I find a determinant. This is En. If this is non-zero, then these n vectors are linearly independent. So the determinant is equal to 0. That means E1, E2 to En are linearly dependent. If not 0, then they are linearly independent. And for this matrix E, we can also write it on the matrix E. E11, E21 to En1. To the end. Here's E1n, E2n to Enn. This is your matrix E. Oh, the matrix. Then let me ask you a question. If E1 to En are linearly independent, then what is the rank of this matrix E? If E1 to En, this is E1, E2 to En, they are linearly independent, then what is the rank? Bonus point, anyone? N? Okay, so if E1 to En they are linearly independent, then the matrix this matrix E has rank n. Well, if the determinant of this matrix E is 0, what does that mean? The rank of E, the rank of E is greater than n or equal to n or less than n. In this case, if the determinant is 0, less than, right? Okay, so now we can apply that to the system, homogeneous system. So this is just a quick review. Test for linear independence of the system. Now the vector becomes the vector of function of t. Here is a function of t, function of t, function of t. And they are also the vectors phi 1 to phi n. Now, if we say that phi 1 to phi n are linearly independent, if and only if the determinant to phi n1t phi 1n phi 2n to phi nn. Oh, still miss one here. Right, this determinant should be equal to 0 or not equal to 0. Linearly independent, so they cannot be equal to 0. And we will say this is equation 5. Any questions so far? I expect there should be a question here. We know the determinant shouldn't be 0, right? But you can see now what is phi 1 to phi 1 or phi 1t to phi n1t, and this vector is a function of time, right? What's the result of this determinant? If this is a function, it is not a number now. If it's a number, easy, right? You can find a number. But now it's a function of time, so one more. No, not this here. Then your result is a function of time as well. How do I know it is 0 or not? Because I have a t, right? So how do we check this equation 5? We can use the we can pick any number of time. Say we can pick any t naught. This t naught is also the open interval. And then we can evaluate this determinant at t equals t naught. Remember that we have finally you may get something t squared plus something t plus something. And now I cannot say that this is 0 or not, so I need to plug in t. So I can just pick t naught to plug in. And this t naught is in our region. Then you will get the scalar to check if this scalar is 0 or not. Right? Alright, so now finally we're going to look at how do we find the solution for the homogeneous system. So here, the general solution for the homogeneous system, I have a phi that is a linear combination of your fundamental solutions, and C1 to Cn are the constants. I can have a matrix omega. This omega is formed by the fundamental solutions. This is phi 1, phi 2t to phi nt. This is a phi 1t. Now the general solution for this homogeneous system is phi equals this matrix omega times c. C is the constants, and we can also put the constants into a vector form. The phi, the omega is called fundamental matrix. And how about the c, the coefficients? The coefficients can be determined from the initial conditions as well. That's straightforward. So if I have initial conditions, then we will write it down as, this is still a vector, okay? Phi to 0. Okay, back to our test. We need to check phi 1 to phi n are linearly independent, and then they can form the fundamental solutions. So here now, and also this is the function of time. How can I know this is equal to 0 or not? Then we will plug in any number like t naught in the region. So here, this is the example. Phi 1 and phi 2. I want to know if they are linearly independent. So we can check say t equals 0. If t equals 0, then I have a determinant t equals 0, 1 minus 2, right? 3 and 1. And what is the determinant for this matrix? 7 and it is not 0. So we know phi 1 and phi 2 are linearly independent. Similarly, for this one, we say we let t equals 0. That'll be easier. You can also have t equals 1. Then you just make yourself in a complicated situation, because you have minus 2 times e to the 3, e to the 3, and something, and you need to also find the determinant. The easier way, because t equals 0, then exponential is 1. So that's why I choose 0. Then the determinant will be minus 2, 1, 1, 0. And this is minus 1. The determinant is minus 1, not 0. So they are linearly independent. Since they are linearly independent, then we can write a general solution. Well, suppose you found the fundamental solutions phi 1 and phi 2, and then they are linearly independent. Then you can write the general solution. Phi is C1 phi 1 plus C2 phi 2. You can rearrange this. You get the omega times the coefficient C. And here the omega is phi 1 formed by phi 1, phi 2. And the matrix, the vector C is C1 and C2. Now your solution, C1 phi 1 plus C2 phi 2 it can be also written down as a fundamental matrix phi omega times constant C or coefficient C. Omega and C. Any questions for this one?